Hello everybody. I'm very happy to be here with you. This is the first PyCon in Greece, so it's really an honor for me to be here. Well, my name is Antonis Markoulis, and I'm currently a senior staff engineer at Orpheum. Today, I want to share with you how we can solve complex distributed systems problems, and we will use event sourcing and CQRS by familiar Python tools such as the Fast API and the Celery. So, let's start with a real-world problem. And this is a classic nightmare, and probably this sounds familiar to many of you. On Monday, you have a report, and there's a user that's been missing. So Sarah's account has been missing. And after lots of debugging, we lost the whole day. And on Tuesday, we still haven't been able to find out where is Sarah's account. So, what's the problem here? The problem is that usually in the classic architectures, we usually have one row in the database for each entity. Okay. Is that better? Okay. So, what happens? What happens is that in the worst case scenario, usually this row is deleted, so we cannot track anything. On best case, we have a kind of soft deletion mechanism. We might be able to find when that deletion happened. We might be able to find who did it, but for sure we lose the why. And this is very important. So let's say that we have a system that doesn't have the full memory of what happened. And this is a huge problem on many cases. So this is where event sourcing comes into play. And usually event sourcing is combined with the CQRS pattern. What's very important in event sourcing is that we store the events, and the events are the facts. We don't do any interpretation of what happened. We just store the raw event which states the change in the system. With the CQRS part, we have the separation of concerns. So we let's say, perform the writes in one database and the reads on another database. And those two, event sourcing with CQRS, they combine very well together. So, let's go back to those events, those facts. How would this event look like? Well, the event is the one you're seeing on the slide. So probably we'd have an ID of the event, the aggregate ID, which is the user ID that was affected, the type of the event, the timestamp, the schema version, the revision, and also the data. As you can see, we have everything that we need here. We have the full facts, and those facts, they never change. So, how about where we store those events? Usually, what we have here is we have the event store, and the event store is an append-only storage. We organize the storage usually on streams, and we have a different stream per each aggregate. So, for example, if we wanted to see the stream of Sarah, we would have a creation event, then we would have some update events, and finally, we would have the deletion event. So this is the full stream for Sarah. So, what are the characteristics of this stream? Well, it's an append-only stream, so we never update or delete any event. We organize per aggregate. We can replay those events at any point in time and go to a specific timestamp. And we usually mention this event store as the write model. Overall, this stream is the source of truth, and this is all that we need to store effectively. Now, let's go to the world of CQRS and start with the commands. The commands, they represent the intent to change the system state. So, if I want to create a user, I will have a create user command. If I want to change a password, I would have a change password command. The characteristics of the commands are that they express what we want to happen. They have basic validations of the payload that they carry, but also of the fields that they need to have. They're idempotent. This means that we can apply them as many times as we want. And usually they are the entry point for the whole procedure. So it's the starting point for when we want to change the system. Overall, they present what we want to do. And on the other hand, we have the queries. And the queries, they present the intent to read data from the system. For example, we might have a get user account query, or we have a get all users query. The characteristics of the queries themselves are that they are read-only, so they don't alter the system state. They use different models, and this is very important, so we don't query the events. We use a different model, and this is where the CQRS comes into play. And those new models, they are optimized for the specific access pattern. So usually we can have denormalized databases, we can have specific indexes that are just proper for reading. And this is the whole concept. Different models for different purposes. How about the business? Well, the business, it's on the aggregates. And the aggregates, they contain the domain logic, and their main role is to produce new events. So, for example, validations such as an email needing to be unique or a two-short password, etc., those belong to the aggregates. And those aggregates, they have two main roles. First of all, they get up to date by applying events, but they also have business logic methods in order to apply the business logic and produce new events. Now, the final part, this is the projections. And the projections are the entities that actually are being used in order to build those read models. So, for example, if I have an event that a user has been created, I might have multiple projections on this one. So I might have a projection that actually creates the user model, the read model, but I also would have a projection that's about sending an email. So I would create, I would say I would send a welcome email to the user. So the characteristics here are that the projections are event-driven, so they're triggered by events. We can have multiple projections per event, and the most important, they are eventually consistent, so they are updated asynchronously on the background. Now, how everything works together. Everything usually starts from an API, and we have two different, let's say, flows, the write flow and the read flow. Let's start with the writes. And for the writes, what we have is that we need to find the proper command, and each command, it has its own command handler. This is one-by-one relationship. And the command handler orchestrates the process from this point on. So we have the command handler finding the correct aggregate, and then using it getting it up to date, and then using it to create new events. And those events then have two destinations. First of all, the event store, the write model that is. So we store those events, and then we also have the event bus. And this is where projections come into play, because they can get those events from the event bus and ultimately update the read model. So this is how the writes behave. When it comes to the reads, we start again from the API, and we need to find the correct query. And then each query has its own query handler, and this is again one by one. So the query handler is the one that interacts with the read models, and we can retrieve the data from the read database. So we have same APIs, the same entry point, but two different paths for writes and reads. We're in a PyCon, so let's show some code here. And I'm going to start again from the API part. Luckily, the ecosystem of Python, it offers a huge variety of APIs. I'm going to stick with FastAPI because it's very, very fast, and also because it's very agile. We can adapt any kind of architecture we want in it, and it's really easy. Also, what FastAPI does very well is that it connects very well with Pydantic. And we can use Pydantic, which is a very, very powerful tool, in order to handle the payloads, the queries, but we also can handle the commands and the queries. So everything is a Pydantic model. And this gives us out-of-the-box validations and other checks. So, as you can see in this slide, we have the two different paths. So we'll start from the first one, the read one, the write one. All we need to do is to leverage FastAPI's dependency injection mechanism. So all we need to do is to pick the proper command handler, populate the command from the payload, and then we can call the handle method of the handler. And that's it. Very minimal API, very thin layer. Same applies with the API for the reads. So we just need to get the query handler from the dependency injection and call its query handler. That's all that is in terms of the API code. Very, very minimal, very, very thin. Let's deep dive now and let's see how a command handler looks like. Well, a command handler is a classic Python object. It's a Python class. And usually all we need to implement there is the handle method. And the handle method, it takes one command. So what we need to do in a command handler is to, first of all, retrieve all the events for the specific aggregate, apply them to the aggregate so the aggregate is up to date, and then call a business method in order to produce the new events. Then we need to send these events to the destination. So we have the storage to the event store, and also we have the dispatch to the event bus. Usually here we might use a unit of word pattern because we want this to either succeed as a whole or fail as a whole. How about aggregates? This is where the heart of the business lives. Yet again, the aggregates are pure Python classes. So the aggregates usually what they have is they have an apply method which takes events and applies them in order to make the aggregate up to date. So in the apply method, we would usually have a long else if, mechanism in order to apply the proper business logic method. What we also have is the business logic itself. So we might have a change password method here where we run the validations, the business logic, and we would check whether the password being very, having too many characters or too low characters. But we'll also, this is the part where we produce the new events. Now, let's go to one of the most interesting parts of this whole code organization. We need to send the events to the event bus. And this is where Python, it offers a really, really powerful tool, which is Celery. Celery is a distributed task queue. And how we want to use it? Well, what we want to do at this point is, first of all, to add the messages to the event bus, but we also want to somehow trigger the projections from those events. And Celery is very good because it can do both at once. So you can see my Celery event handler. All we need to do here is to implement a dispatch method, which actually what it does, it iterates over the events that we want to dispatch. And for each one, it reads the configuration where we have which event maps to which Celery task, and it just calls the Celery tasks. So this is very, very powerful, and it enables all the async processing within the projections. Now, how about the Celery tasks themselves? Well, this is the code of Celery task, and you can see the same patterns that are being applied in the API layer. You can see the same patterns being applied here. So what we have here? We have a dependency injection mechanism. Unfortunately, in Celery, we don't have the depends. We don't have this kind of functionality. So we need to do the dependency injection manually. So what we want to do here is to get the infrastructure factory and from it retrieve the proper projection. Once we have the projection in our hands, what we need to do is to call its handle method and pass the event. It's really, really easy. The code is really, really minimal. You can see in this part that we have to use an async to sync method. Well, this is some magic because Celery doesn't actually support asynchronous code at this point. So in order to run asynchronous code, we don't want to write both synchronous and asynchronous code. We have one flavor. So in order to run asynchronous code from Celery itself, we need to use this async to sync. Other than that, we have a very, very reliable mechanism of processing the events. What's also interesting about Celery is the fact that it offers a huge variety of capabilities. What's the worst that can happen in event sourcing architecture? It is to lose an event. We cannot afford to lose events. And this is where Celery comes into play because It's really easy to implement retry strategies. We can implement late acknowledgement patterns. We can implement jitter in order to not have all the retries at one time. We can also have exponential backoff. So all these things, they come naturally from Celery. We don't have to write any code. We just need to configure. And this is what makes the whole architecture very, very powerful. And this is why we need to use it. So this whole combination of ACK-Slate, retries, and it can handle all the real-world failures. Now, one last thing about the code itself. This is about the projections. So, as we said before, the projections, they are triggered by the Celery tasks. Let me go back to this one. So you see the handle method here on the Celery task. So the handle method, all that it needs to receive is to receive an event, which is, let's say, a user-created event in this case. And then we need to use a repository-like pattern to just take this event and store it to the read model. So this is how we update the read model. Yesterday, I think, or the week before, Celery also supported Pydantic models. So this is a huge win because we will be able to somehow make this part, because at this point you can see that I was passing the event as a string, as a dictionary. Now this is fixed and we can also use Pydantic validations in the Celery tasks themselves. So this is really amazing. Overall, as you can see, the projections are being tackled asynchronously and they update the remodels. So this is why we do the database save of the user data. Now, this is how everything wraps up. So we have the commands being calling the command handlers, the command handlers using the event store to retrieve, to get up to date the aggregates and produce new events. The events that are then triggered to the two destinations, the event store, the event bus. From the event bus, we have the projections, and the projections update the read model. And this is the full life cycle. Now, let's go to the most interesting part. What about reality? You can see that the code that I described is really, really simple, and it makes sense to apply it. It's really easy. Well, in reality, things don't go that well. And we have lots of issues. I can talk for an hour about issues that we'll face with events, with production, with event sourcing. However, I have decided to focus on 3. And let me start with a nightmare, the eventual consistency. So, let's start with an example. We have Sarah. I really love this name. And Sarah, she wants again to change her name, and she wants to remove that extra H. I know sometimes we write it with an H, sometimes we don't. So Sarah wants to remove that H. And of course, we have a form in the front end, and Sarah edits the name, and she hits the submit button. What happens is that when she hits the submit button, nothing erroneous happens, and the screen refreshes. And Sarah sees again Sarah with an H. And she's really confused. What's going on? This is the classic problem of eventual consistency. And it happens not only on event sourcing, but in other architectures that usually have async processing. So, what's happened on the background? What really happened is that even though when we hit the submit button, the actual event was populated and it was stored in the event store, and this is why we got the successful response, the read model didn't get updated. And the front end, after submitting the form, it called the backend in order to get the new user. And the user hasn't been updated because the projection hasn't been executed. So, how can we handle this one? Well, I've seen 2 approaches. Let me start with the most, let's say, naive. And this is called optimistic updates. This is something that I really like because I don't have to do anything as a backend developer. Everything happens in the front end. And what actually happens here is that when we hit the submit button, the front end, in the case that it receives a successful result, it says, well, the event has been persisted, eventually this will happen. So let me act as if everything works as planned. So the frontend doesn't perform the GET request, and it shows the updated value. So everything works like a charm. I know you're probably thinking, what happens if a user refreshes manually the screen? Normal users, and I don't mean QA engineers, I mean normal users, don't do that. I didn't have such a case. But also, what we actually want to do at this point is that we want to make sure that our, let's say, consistency is consistent within some seconds. And we might have an SLO for this one. So we might count how much time it takes from writing to the event store to updating the read store. And in simple applications, this can be 5 seconds, 8 seconds, something like that. So the case of forcing an update and doing this in less than 5 seconds, well, it's pretty, let's say, it doesn't happen. Now, let's go to a more, let's say, advanced technique. What if our update of the read model, it takes hours to be performed because we want to run a machine learning algorithm in order to update the read model. And the projection is very, very complex. This is where we use the outbox pattern. And you can hear the outbox pattern a lot because in other architectures that don't have Celery, they use it by design. But what we actually do here is that we have a table in the database that has each event and whether it has been processed or not by projections. And what we do here is that we expose this table to the front end. So the user, he can see or see what's the status of this projection. So this kind of, it alters the whole nature of our application because the users, they need to know that everything that you do is managed on the background. So this changes the experience. And in many cases, this is totally acceptable. So overall, there's no solution to the eventual consistency issue. We just need to have thoughtful UI design and work together with the product team and pick one of the two solutions. My favorite one, the performance issue. Well, as we said in the beginning, the event store is an append-only storage. So as time goes by, we tend to accumulate more and more and more and more events. And this does never change. So what we have here is a classic example of slow performance. So let's say that we have a user that he wants to change his password, but he's a very active user. He has lots of events on his event stream. So what we need to do again is we go to the command handler and we pick those 10,000 events, and then we need to apply 10,000 events. This takes 5 seconds. And 5 seconds for a password change, well, this is totally unacceptable. So how can we tackle that? Well, the solution to this one is snapshots. And how do we handle snapshots? Every X events, we just store in another database a snapshot of the aggregate itself. So for this specific case, what we would do is that we would get snapshot of this user and only apply the remaining events. And this is very, very agile because it is up to us to select how soon we will get a snapshot or let's say if we have multiple snapshots, and this whole thing depends on us and we have all the capabilities to do so. So in this case, we'd only have to apply, let's say, 50 events, and this would make the performance from taking 5 seconds to milliseconds. And this is how we can solve the whole performance with the snapshots. Overall, it's a very safe way of rebuilding the state efficiently. Now, the third one. Let's go back to the first slide, because we had an actual problem. We lost Sarah's account and we were not able to find what happened. So this is where event sourcing thrives, and it's on debugging. So what happens here? You can see the timeline. So we have the Sarah's account reporting to be missing, and then we can do what? All we need to do is that we need to get those events from the production database. If we have those events, we can make the debugging story into a unit test. How is that? We just need, you can see that I'm using a PyTest test case here. What do? Well, we initiate a user aggregate, a user, so we have Sarah. We apply the events from the production, and we get to the point where the event is supposed to be applied, the deletion event. We can then apply the problematic event, and we can assert the state after the event, so we can know for sure what happened. We can do that very easily just by applying the events, and we don't need any kind of infrastructure for that. This can be tested in isolation, and we can have thousands of tests like this. What's really important here is that we can test both applying problematic messages, but we can also apply the business logic methods. So it's really, really easy to test the core of our application without any involvement of infrastructure. So what's really important is that we can make the debugging a test case. And we can even predict bugs by using this one. Just by applying random events from our database, we can create real test cases. And finally, the time travel. We can go at any point in time and debug. So we're not able only to debug what happened now, we can go in the past. And I know Monday is, let's say, very close to us, but we can debug what happened 2 years ago. And this, for systems that require auditing, well, it's really, really important. Now, let's perform one summary. First of all, you can think that I didn't mention anything about infrastructure. I didn't mention anything about databases, about event buses, about anything. Why is that? Well, personally, I believe that we need to start simple. We don't have to use fancy event stores. We don't have to use Current or Event Store, it was called. We don't have to use Kafka. We don't have to use MongoDB in order to be our read database. We don't have to do that. Start simple with technologies that you know. And on 90% of the cases, this is more than enough. And if it happens that you cannot, that they're not enough, you can easily switch because the architecture is not, it allows to do so. So another thing that I want to add here is about Kafka. Most of people are using Kafka in event sourcing because it combines the event store with the event bus. This is a counter pattern. Don't do that. Now, is event sourcing the solution to everything? Not really. If you just want to create a simple CRUD API, don't use event sourcing. Probably logging is enough for you. You don't have to use event sourcing. Also, if you have a trading system, which is high frequency, and it probably requires immediate consistency, I would advise you again to not use event sourcing for this kind of systems. Finally, and most important, if you have a team that doesn't have experienced people, I would again advise you to not go to event sourcing because it has, let's say, it needs too much of experience. So I would advise to start with a proof of concept, test what happens, and then move on to actually implementing this one into production. However, if you're not on these three cases, go for it because you will gain complete audit trail and you also gain the time traveling capabilities. You have debugging superpowers. You can go anytime with real production data. And you also have the scalability because of eventual consistency. You can have multiple workers working on the background. You can have everything like that. Finally, you can use Python. The ecosystem, it does provide you with everything that you need in order to implement. So you don't need to go to Java. Python has everything that you need. Thanks a lot for everything. You can find me on GitHub, but also on GitHub, I have a full example, a full implementation of event sourcing pattern. So you can see how this can be applied. So feel free to see the whole pattern. That's all from me.